On today's episode, is reusability really the answer for low-cost spaceflight? Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. We've all seen those remarkable films of SpaceX first-stage boosters flying themselves down to a soft landing on barges or to Cape Canaveral. It's a remarkable achievement to fly something as large as a rocket stage back to a soft landing, a little like balancing a pencil on its end. Now, the SpaceX effort represents the current state-of-the-art and reusability of spacecraft, and it does what the rockets before it couldn't do, actually reduce costs. Now, the Space Shuttle program was designed specifically to reduce the high cost of heavy lift to orbit, originally with an entirely reusable design. Now, tight budgets of the 1970s forced a redesign into the form that we're all familiar with solid rocket boosters parachuting into the sea to be towed ashore and refurbished after each flight. Now, the concept worked, but what it didn't do was actually reduce the cost of launching satellites into orbit, and it never replaced expendable systems for satellite launch. But with SpaceX now dropping the price of lift to orbit, the new competitors in the orbital launch race are looking to reusability as a necessity to achieve competitive costs. Now, the Space Shuttle solid rocket boosters proved to be 100% reusable, but as an overall system, the shuttle surprisingly delivered no cost advantage in pounds to low Earth orbit compared to expendables. Now, the SpaceX flyback system is proven and it has reduced costs, but it's not the only route to reusability. Rocket Lab, a small sat launcher that has captured a notable portion of the launch market with its Electron vehicle, has designed a novel first stage that after burnout will deploy a parachute and be captured mid-air by a helicopter for flyback and refurbishment. Now, mid-air recovery of space vehicles is not new, with spy satellite payloads hooked out of mid-air by cargo aircraft 60 years ago, but rocket stages are large and heavy, so it will be a noteworthy achievement if Rocket Lab pulls this off. Now, the other major company in the heavy lift market is United Launch Alliance, makers of the large Vulcan system. Now, Vulcan will use complex Blue Origin designed first-stage engines, and ULA is looking at a novel form of reusability, the severing of main engines from the airframe and mid-air parachute recovery of the engine and avionics package. While this idea sounds difficult and complex, involving explosive separation of engine mounts, fuel and electrical lines, there are sound economic rationales for using this approach. Engines represent over 50% of the cost of a Vulcan first stage, but account for only 1/4 of the mass, making the engines the highest value per unit mass for recovery and reuse. It may also be possible to package much of the booster's avionics into the engines as well for further savings. And for mid-air recovery, capturing a mass that's 1/4 of the launch weight of the stage looks attractive too. The SpaceX, ULA, and Rocket Lab reusability systems are all different, but all face a similar challenge: the cost of refurbishment versus new build. Now, SpaceX will likely have the lowest cost since they require minimal recovery infrastructure to soft land their stages. But they pay a serious performance penalty for doing so, reserving a significant proportion of propellant weight at launch for flyback and carrying that extra weight of the landing gear and the associated hardware. For high-performance launches, SpaceX omits that reusability capability. Now, Rocket Lab can use most of its first-stage fuel, but still carries a weight penalty in the parachute systems, and it's not known if mid-air helicopter recovery of something as large as a rocket stage can be done routinely. The ULA approach is especially interesting because they simply blow off the expensive bits, which should make them easier to capture. To make it work as a system, however, it will require low-cost mass production of airframes and tankage to minimize the losses in discarding 3/4 of the booster's weight into the ocean. So are any of these systems ideal? Well, probably not, but the ideal system would be expensive and would likely look something like the original Space Shuttle booster concept: a rocket-powered glider that would fly itself back to a runway, much like the orbiter did itself. That idea, however, proved cost prohibitive in the early 1970s, and it would be just as expensive today. But right now I'm watching Rocket Lab. They're small, launch small satellites, but they have a healthy order book, and their system promises to offer the reusability of SpaceX with none of the weight and performance disadvantages of flyback systems. Well, that's it for today's episode of End of the Line, brought to you by Engineering.com. If you like this show, be sure to subscribe to our channel and click on the notification bell for our next episode. For our deeper engineering video series for the manufacturing professional, visit Engineering.com TV to watch exclusive shows like Manufacturing the Future, not found here on our YouTube channel. The link is in the description below. Thanks for watching.